Now, I didn't mention it before, but anytime a light ray hits a boundary between two objects, there is refraction and there's also some reflection. Okay, depending on the object, there may be more or less light that's reflected, or depending on the materials in question and whatnot, there may be more object that's reflected, more that's refracted. Now, if we say that object 2 has a smaller index of refraction than 1, this light's going to bend away from the normal. Okay. Now, if you think about if this beam gets further and further from the normal, this one will always be further from the normal than this one is, and eventually there won't be any space left for it. The largest angle of refraction possible, theta 2 has to be less than 90 degrees. If it hits 90 degrees, then it's not really entering into that material. So if we establish that cap, we can say n1 sine theta 1 equals n2 sine theta 2. Well, if theta 2 is a max of 90, we can say sine theta 2, of course, has a max of 1. So we can say n1 sine theta 1 equals n2. So sine theta 1 equals n2 over n1, applying Snell's law. But then if n2 is greater than n1, then, so if n2 is greater than n1, then this doesn't work, right? So n1, in this case, n1, in the case of n2, in case of theta 2 approaching the limit of 90 degrees, n1 must be greater than n2, okay? And for theta 2 to get to that limit of 90 degrees, the incoming angle has to be equal to the ratio of their indices of refraction. That's called the critical angle, because if that angle is reached, then there will be what's called total internal reflection. So if n1 is greater than n2, there is an angle where there won't be any refraction. No light will pass into the new material. They'll just bounce back and remain in n1 when the angle of incidence reaches this critical angle. Now, that is useful in a couple different ways, in a couple different things. One application that's very important are optical fibers. Optical fibers, they have a high index of refraction, and light inside, and signals being sent down the fibers, they get this total internal reflection. They just bounce and go along, and they're much more efficient at transferring information than sending electrical signals down a copper wire. You're sending a light ray, and they can carry tons and tons of information, and they're used a lot for information transfer because of that. This is also useful so there's optical fibers, and optical fibers, so they're used for information transfer. They're also used in those kind of snaky sort of cameras that are used in medicine a lot, where they'll stick a camera through an incision and kind of move it around and be able to look at things inside your body using that camera. And those kind of snaky cameras are also used by spies and thieves in movies. I don't know if I imagine that the CIA and FBI and stuff do actually use those kind of cameras as well. But they are definitely used in medical applications as well. Now, one other thing related to this is polarization. So recall that light is polarized when it's reflected. Okay. Now there is a special angle where this polarization is complete, and that's where so when we hit this interchange, some light reflects and some of it refracts. Okay, and the special angle for which polarization is complete is when this right here is a right angle. Okay? And if that is to be a right angle, this is our theta 1, this is our theta 2, that means that theta 1 and theta 2, well, this angle is complementary to theta 2, this angle is complementary to theta 1, and they're complementary to each other, so that means that theta 1 and theta 2 are complementary. If theta 1 and theta 2 are complementary, we get total polarization. I'm not giving you a mechanism, a reason that it happens that way. If you want, you can go back and look at what I said about reflected light polarizing, and in that context, I think it'll make sense. But so the angles of incidence and refraction are complementary, and that's called Brewster's angle, named after a guy named Brewster, I guess. Again, we're starting with Snell's law. But in this case, we know that theta 1 and theta 2 are complementary. So n1 sine theta 1 is n2 sine 90 minus theta 1. And sine of 90 minus theta 1 is cosine theta 1. That's a trigonometric identity. And so if we move this around, divide the cosine over here, that gives us a tangent of theta 1 then is equal to n2 over n1. And that is how we find Brewster's angle. So we have a couple different formulas related to Snell's law. I've got critical angle, Brewster's angle, and then Snell's law itself. And these are all formulas that we can use to calculate things related to refraction and total internal reflection, and then this total polarization.